All right. So we've talked about some of the simple or metallic structures, a lot of them being cubic. And we talked about atomic packing factor, which describes the ratio of space filled. But I also want us to go through density calculations. And so this would be a theoretical density calculation based off of the structure that element or an atom or an alloy, whatever it may be, is. So you're probably familiar with how we define density, usually defined as rho. All it is the mass over volume, right? How much mass is in a given volume? That's density. And that's what we're going to do here. The only difference is because we're looking at a crystal structure, and we think of crystal structures as going off in infinite, you know, lengths and so forth, we want to constrain it to given volume. And so again, you see the unit cell. So we're going to define the mass of atoms in that unit cell, and then by the volume of the unit cell. So we're just using the unit cell as our kind of volume and how much mass is in that volume. So we can kind of formalize this more in the equation that you see here. So I'll mention right now, this has a summation. So the sigma that you see here, it has a summation. But since we're only dealing with one type of atom, you don't have to do this. But in the future, if we're dealing with something that has multiple types of atoms, for example, an alloy where we may have we may have iron and carbon, then you'll have to sum the the iron part and this carbon part. So for now, though, we just need to know the number of atoms in the unit cell, so that's N, multiplied by the atomic weight, and that's going to be in grams per mole. Right? So atomic weight we can get from the periodic table, number of atoms we can get from the structure. And we saw that with simple cubic. And then the volume of the unit cell is just the volume, right? So for cubic, it's A cubed. For hexagonal, it's going to be different. But for cubic, it's going to be A cubed. And then there's going to be a factor of Avogadro's number because we need to convert, because we have grams per mole and we want to talk in atoms. So we have to use Avogadro's number. So that's where we get this equation. So this is basically a units conversion down here. All right, so let's go ahead and do this, right? I'm going to start you off with an example and see how well you do. So this will be on the quiz. So this is BCC, Chromium Cr is a BCC metal. So I put the picture back up there for BCC. I've given you the atomic radius here, and also the atomic weight, so you don't have to go look it up from the periodic table. So what I want you to do is, using the equation from the previous slide here, see if you can calculate the theoretical density using these numbers and using what we've talked about, particularly in the atomic packing factor equation. Some of that will help you with determining the density here. So do that, fill it in the quiz, and come back and we will discuss the results. Okay, so I switched over to the paper so that we can look at the density of chromium. And so I copied down the data that we were given. So it's a BCC, so I redrew it here. We were given the radius of a chromium atom. We were given the atomic weight of chromium. And then the Avogadro's number is 6.022 times 10 to the 23rd atoms per mole. And then I replicated the density equation. So if we kind of go through this, again, there's no summation on this one because we only have one atom. But we need to know the number of atoms, chromium atoms, the atomic weight. So we have that over here. We need to calculate the weight, the number. So that's what we'll have to do. We have to calculate the volume of the unit cell, and then the constant Avogadro's number. So we've got that. So let's start with the number. So if chromium forms into this structure, then how many do we have? So we know that BCC has everything on the corners. So that's going to be an eighth of an atom on each corner, and there's 8 corners, right? So we know that's 1. Plus, the BCC part is body centered. So there's 1 right in the middle, which means we have an extra 1. So our number of chromium atoms, or number of atoms in any BCC structure, is going to be 2. So we know this, right? We know this part. And then we know A because we're given this, or we can look it up in the periodic table. And then we have this. So the last part now is the volume, right? So we know that this is A. So we already know that the volume of the unit cell, which we're calling VC, is A cubed, right? Volume of a cube, A cubed. However, this isn't good enough, right? Because we don't know A for this structure. But we do know R, right? And so we're going to use that last portion of the atomic packing factor problem-solving process to be able to get a relationship between A and R. Because we know R, and we know we want to get it in terms of A. So if this is A, and again, the radius is R, we can get that relationship. And all of these problems, you find where they're in contact. So if you go back to the slides on BCC, you'll see that the direction of contact was along diagonals, right? Any one of the diagonals is where you have contact between atoms. So if we look at that diagonal, right, we have 1 radius, 2 more radiuses here for the, sorry, I'm covering up with my hand. We've got 1 radius up here, then it goes through 2 more radiuses here, and then another one down here, right? So that length is equal to 4R. So now we just need to know what that length is, and we need to know it in terms of A. So the way I recommend doing this is, if I think about the base of the cube, we know this is A and this is A, right? And if we do Pythagorean theorem, we should be able to get that this is square root of 2A, right? Pythagorean theorem. A squared plus A squared equals, and then you get square root of 2A, right? If you solve for that hypotenuse. So we've got that, right? And then we can, so basically we've got the diagonal here. Oops, sorry, I'm covering it up again. So we've got the diagonal here as square root of 2A. So we can draw another triangle where the base here is square root of 2A. It's this portion here. Then this is the back portion here, which is A. And we're trying to solve what this is, which is our diagonal, right? This is the diagonal we're after. And so, again, what we can do is Pythagorean theorem again. And so in this case, if we do that to this, we would end up getting square root of 3A for this. And the reason this is important, because we know that there's an atom centered here, an atom centered here, and then one in the middle, and even though I drew it badly, there's no empty space. These 3 atoms are touching. So we know square root of 3A is equal to what we saw before, 1R, another, and another down here, so 4R. So that we know for BCC, if we look at the way that atoms touch in BCC, we know that A is going to be equal to 4R over square root of 3, right? So, and this is for BCC. So this is a relationship that our book gives us. But I think it's important that you know where it sort of comes from, and you can solve it for a given structure. So the main idea here is that we find a geometric line where things are touching because there's no empty space, so that we can relate the lattice parameter, so an edge length or something like that, to the radius. And that's what we've done here by using this relationship. So now we've got everything we need to know, right? We know that this is the volume of the unit cell is a cubed, so we can plug in this expression down here, 4r over square root of 3 cubed. And we know r, and so we can solve it now. So let's put in all those numbers. So we've got 2 as our number of atoms. We know the atomic weight given to us, 52.00 grams per mole. On the bottom, we have the volume expression. So 4 times the radius, so 0.125 nanometers. We might go ahead and convert this though, because we typically want this in different units, right? Because right now we're going to have this in nanometers, and nanometers not super helpful. So we would rather have this in terms of centimeters or meters. So gram centimeter cubed is a very common unit for density. So we can go ahead and convert that into centimeters. All right, so the unit conversion here then, nanometer is 10 to the minus 9 meters. So if we convert that into meters, we would get 10 to the minus 9 meters. And then, like I said, centimeter is more common. So there's 100 centimeters in a meter. So basically we're going back to 10 to the minus 7 centimeters. So we can use this. So the basic idea here is, always check your units, see what you're getting here. So we're going to use 10 to the minus 7 centimeters in the volume expression down here. That's all over square root of 3. This is cubed, and then multiplied by Avogadro's number. So 6.022 times 10 to the 23rd atoms per mole. So at this point, if we plug all this in, we're going to have grams. The moles cancel out, and we're going to be left with centimeters cubed. So our density here, when we plug this all in to our calculator, is going to be 7.18 grams per centimeter cubed. So that's our density. So this is our theory. This is what we're predicting for chromium based on the fact that it's BCC and we know the radius of chromium, right? That's how we're getting this number. If we actually calculate this to the actual density that chromium has, so if you go up and look what that is, it's actually 7.19 or somewhere along those lines. So it's this calculation is very close. So the idea we have here for chromium is really close. It's basically spot on for what we have. So this is how you would do a density calculation for a single material. Again, keep in mind that this is a summation. So if we're starting to look at structures and no longer are all of these the same atom, so all of these are chromium, well, if now we start to replace them and look at ceramics where we have multiple, then what we're going to do is count each of those separately. So we're going to count up the number of chromium and then count up the number of the next thing and the next thing, and we're going to take the summation of this number times atomic weight term. But everything else would be the same in those calculations. All right, so we've taken a look at the density of chromium, and so now let's look at kind of general trends. So in general, the density of metals is higher than the density of ceramics, which is higher than polymers. So let's take a look at this chart. So this is density in the units we just used, so grams per centimeter cube. And you can see here that metals have a pretty wide range, anywhere from about 2 grams per centimeter cubed all the way up to 20. So those kind of noble metals like platinum and gold that we see up here, but also pretty lightweight metals like magnesium and aluminum. Ceramics kind of fall on the lower end of metals, and then polymers here are on the low, much lower than can be much lower than those two. And you can kind of see here they're somewhere in the neighborhood of 1 gram per centimeter cube, which is the density of water. So if you remember that, you can see that some of them are less dense than water and some of them are slightly higher density than water. Also, put composites up here. Since composites are mixtures of polymers and ceramics or metals, then those tend to be around polymers, but also can be quite a bit lower, such as natural composites like wood. So let's look at why this is the case. So we've just looked at metal structures, and we see that they are tend to be very dense, right? BCC, FCC, HCP, those were all fairly close packed. They also tend to have atoms with large atomic masses, and so that's why we get high densities. Ceramics, on the other hand, are slightly less dense packing. This is the next category of structures we're going to look at, and oftentimes have a mixture of metals but also lighter elements like those non-metals. And polymers have low packing. Like we kind of mentioned in the amorphous section, they can actually be amorphous or a mixture of amorphous and crystalline, and they deal with those low elements in most cases, like carbon, hydrogen, oxygen. So they tend to be on the low side. And then obviously composites going to kind of have intermediate values because they are mixtures of these different classes.